All right, welcome back. So today we'll be looking at the chapter 2, still on geometric optics and imaging. So the focus today will be on imaging. So we know that if you have a plane mirror, you can actually form images in the mirror, right? So the way to do is to visualize your image on paper. Um, suppose you have a plane mirror and then you have your object over here. Now, how can you identify where's the location and the size of your image? So it's to use ray diagrams. So basically, you'll pick a point on your object, and then coming from that point, you have two rays coming out of that point, hit on the mirror. Then you apply law of reflection, which instance angle equals to the reflected angle. So then you back extended the two reflect rays. So then these two rays, extension of them will intersect behind the mirror. So then that's the location of the image of that point of the object, okay, in the mirror. The same thing you can do every other point on the object, so then you can find the image of that point of the object. So typically you'll just do like at the bottom of the image of the object to pick a point there, and then pick a point on the top of it. So then each point you draw two rays out of that point at slightly different angles and hit on the mirror. You get reflected rays and then back extend them to find the image. Okay. So according to that, so then let's take the top of the object here as the example here. So you get one ray up, go up there. So we'll just look at one of the rays, and then it get reflected into your eye. So then back extended. So this is where the image of the top of the object will be. Okay. So then, according to geometry, these two angles should be the same because according to law of reflection, your incident angle should be equal to your reflected angle. Okay, so as a result, so this angle then will be equal to this angle theta. Okay, so these two then are the same. So these two angles will be the same. Now, if you draw a horizontal line across connecting the image and object, the top together. So then this is a horizontal line, which is perpendicular to vertical. So these two are then identical triangles. So the distance from your object to the image then is the same, or to the mirror is the same as the distance of your image to the mirror. So DO equal to DI. And the angles are the same. They share this one side, so they are identical triangles. Okay. So images will be then equal distance from the to the mirror as compared to the object to the mirror. Okay. Also, other things you can actually see from the this figure. So then the image is upright. The image is upright. Okay, to the object, okay, in that sense. You can also have a few mirrors. So if that's the case, so then look at this, if this is object, right? So for the first mirror, it will form an image there. Now, the second mirror will also form an image, okay? So the image in the second mirror actually will then have an image in the first mirror. The same thing, the image in the first mirror will actually have a image on the second mirror, which is not showing in the figure here because it's out of the paper. Okay, so in that sense, so you'll get actually multiple images. Okay, if you have multiple mirrors next to each other. If you have a corner reflector, which consists of two plane mirrors perpendicular to each other, then an object will produce multiple images. Okay, so in this case, there's an image in mirror one, there's an image in mirror two. Okay, and there will be image of image, right? So image of this guy, image one in mirror two, in that sense. And then also, if you can see at different angles, you'll also see different more images in that sense. Okay, so you also create multiple images in that sense. All right, so that's on the image formed by plane mirrors. Now, in our daily life, we will also use other kind of images, right? So in the morning, you use plane mirrors. When you are driving your car, you will use then actually a spherical mirror. Okay, so the mirrors in your car, the side mirrors, the rear view mirrors, they are all spherical mirrors. You don't realize, but they typically have a small curvature. Okay, so that if you don't look carefully, you will not be able to see it. Okay, so spherical mirrors are made of out of curvature by making either the inner side of this curvature as a mirror or the outer side of the image, the piece as the image mirror. So if the outside is mirrored, then it's called a convex mirror. Okay, so it's kind of like having a convex shape on that side. If the inside mirror is called a concave mirror. Okay, so it depends on which side of this part is made as a mirror. Okay, so let's take a look on the two scenarios. So in the drawing, you typically see if there's one side is darker, okay, so that's the reflecting surface. So this is then a concave mirror. On the other side here, this side is darker, so this is a reflecting side of the surface. This is a convex mirror, okay? So there are a few key terms here. So from the center of the curvature to the middle of the mirror, this line is called the principal axis. Okay, so this is center of curvature. This is the principal axis, or also is called the central axis. So they are the same. Okay, central axis or principal axis, they are the same thing. All right. So and the distance from the center of curvature to the mirror, then apparently that's the radius of the sphere, okay, of the curvature in that sense. And then the same here. Okay, so we typically use C to denote the center of curvature. Okay. So for the convex mirror, okay, if you have parallel ray hit on the surface, then the parallel ray, that means parallel to the principal axis or center axis. So then they will actually, when these rays are reflected, they meet at a common point called focal point. Okay, so we use F to denote focal point, and then the distance from this focal point to the mirror is called the focal length. For the convex mirror, if you have parallel rays to the principal or center axis, when they get reflected, they do not actually merge at the common point. But if you back extend then those extended lines from the reflected rays, they actually will intercept behind the mirror. So then this point is the focal point for the convex mirror. Okay, distance from this point to the mirror is called the focal length. Okay, so this is the F. Okay, again for notation. Okay, so C for center of curvature, F for focal point. For a convex mirror, so because the focal point is where the reflected rays, they do not actually meet, so it's called then a virtual or it's called its length, for the focal length of the mirror is called negative. Okay, and then for the concave mirror, because the reflected ray, they do meet at the focal point, so the focal length is actually positive. Okay, and it can be proven from geometry that the focal length for the concave and convex mirror, they are both 1/2 of the radius of the curvature, but for convex mirror is minus of 1/2. For concave mirror is 1/2 of the radius. Okay, so you can see from this figure. So typically the curvature is very small, so that means when you are drawing a line from here to this guy, okay, any point, so this is normal direction, and the curvature is very small, so then from here to here, this instant angle should be small. Okay, so think about a very small curvature, so kind of like almost vertical, right? So in that sense, so this angle will be very small. Okay, so because the law of reflection, so this angle and this angle should be equal to each other. All right, and if this angle is small, then these two, this side and this side, it's very close to this line. Okay, and this is parallel to the center axis, so this then will be also theta. Okay, so for a triangle like this, consists of this dashed line, this and this one. So this side should be equal to this side because this is theta. This is also theta from geometry. Okay, so the two sides are the same because these two angles are the same. And these two are very close to this one, so it's almost this plus that will be equal to this guy if your theta is approaching 0. Okay, so then that's what happens. So for a small curvature, then you can approximately say this side plus this side is equal to this one. Okay, and this is R, this is this side and equal to that guy. If theta is equal to 0, so then you're almost approaching this. So this line and this line will be almost the same. So the focal length then is equal to approximately equal to 1/2 of the radius. Okay, so the same thing here on the other side. Okay, so according to geometry, you should be able to also conclude the same thing. You look at this triangle there. So this should be also theta. This should be also theta. So if angle theta is small enough, then focal length is equal to 1/2 the radius. Okay, but minus. Okay, so the sign of plus or minus is just a convention. So if you have convex mirror, because the reflected beams, they do not actually meet at the focal point, so we call the focal length to be minus. Okay, for the concave mirror, the reflected rays actually do intercept at the focal point, so we call it actually positive for the focal length. Okay, so it's just a convention for the sign. All right, so to produce an image by either concave mirror or convex mirror. Okay, so we will take an example for the concave mirror. So you use 3 principal rays. So the first ray is called the parallel ray. So that means this ray comes parallel to the principal axis. Okay, and because of that, you will actually reflect through the focal point. Okay. The second ray, so this is called P ray. The second ray is called focal ray or F ray. So that's the ray coming through the focal point, hit the mirror, and you will get reflected back, right? So in this case, it's parallel to the principal axis. So this is the F ray. Center of curvature ray, so it will go through the center of curvature, hit the mirror, and get reflected right back in the instant direction, but reverse way, because then from the center of curvature to the mirror, it's in the normal direction, so get reflected right back. Okay, so in the figure, so this is what the 3 rays look like. So P ray parallel to the principal axis hits this guy, will get reflected through this focal point. Okay, the focal ray hits this one, will get reflected parallel. Okay, so this is basically reverse of that. Okay, because the ray passes are reversible. Okay, so if you can go here through that, then the other way around should be also true. Okay, so if you have a ray goes here and then it should reflect back. Center ray, C ray, and because this is normal direction, hit here, will come right back. Okay, so you can use these three principal rays to find the image. So actually, 2 of them will be sufficient enough. Okay, so pick any 2 of those 3 rays and you'll be able to find the position of your image. Okay, so we'll take a look on an example here. Or actually, let me see here. This is one of the, or a couple examples. Okay, so for the concave mirrors, okay, so there are different scenarios depending on where your object is. Okay, so then you actually get the images differences in size. Also, difference in type as well. So sometimes you get reduced image, which means the image is smaller than the object. Sometimes you get enlarged image, which means image is greater than the object. And then sometimes you actually get a virtual image. Okay, so that means it's not real image. So let's take a look on each of these three scenarios one by one. So if your object is beyond the center of curvature to the mirror, so that means the distance of the object is greater than twice of focal length, because this is twice of the focal length, one focal length, two focal lengths. Okay, so if you are there, so let's use two of the principal or two of the three rays, P ray parallel to the center exit, so it will go through the focal point. Okay, the second one, let's use the F ray, goes to the focal point, so get reflected parallel to the center exit. So these two then they intercept over here. So then this is where your image is. Okay, so the location of it, you pick the top of the image of the object. So then this is the top of the image. Okay, so it appears to be upside down in this case, right? So this is upside down. So the two reflected ray, they actually do intercept here. So that means it's a real image. Okay, but in this case, you can see this one is larger than this guy. Okay, so the image is reduced image. Okay, now if you move your object closer to the focal point, in between the center of curvature and the focal point, again, use the two rays out of the three principal rays. So P ray parallel get reflected through the focal point. F ray through the focal point get reflected parallel to the center exit or principal exit. So then these two will intercept over here for the top of the object. So then your object will be actually from here, this being the top. So it's inverted, okay, upside down. In this case, again, the two reflect beams, they intercept over here. So you get a real image, okay? So that means you can actually capture the image on a screen. And it's an enlarged image compared to this guy, okay? So if your distance of objects is greater than twice of focal point, you get actually real image, but inverted, reduced, okay? If you are in between 2F and F, you get the enlarged image real as well, okay? Inverted, upside down. And if you get, if you are in between, or if you move your object closer to the mirror in this case, now in between the focal point and this, okay, again, you can use the two rays, okay? So in this time, we'll use again F ray. So F ray appears to be coming off from this guy. So you connect the F ray to the top of the object and then extend it, okay? So this is the F ray. So it should get reflected back, but parallel to the principal exit. And the second one, you can do the principal or P ray hit here, you will get reflect back that way. Okay, or you can do a center of curvature of C ray. So C ray connecting C with the top of the object hit there will get reflect backward. Okay, so these two rays, you can see they kind of diverge. Okay, when they are reflected, but in that case, they do not intercept on this side, okay? The physical rays do not intercept, but if you back extend them, then they will actually, the extensions will intercept but behind the mirror. So because this side is mirror. So then you actually get a virtual image in this case, because the rays do not intercept, but they appear to be coming from a common point over here behind the mirror. So then this is where your image will be. Okay, so in this case, you get a virtual image. Virtual image is upright. Okay, so if you don't know, just remember that virtual image is also upright. Real image is always inverted. Okay, so and in this case, it's enlarged image compared to this guy. Okay, so this is the distance of the object to the mirror. This is the distance of the image to the mirror. All right. You can do the same for the convex mirror. Okay, so you can also use three principal rays, the F ray, the C ray, the P ray. But in this case, if you have a P ray hit on here, so then it will get reflected back. But this reflected ray appears to be coming from the focal point. Okay, so that means connecting this point to the focal point, and then the reflected ray will be in this direction towards on the object side. Center ray will hit the mirror and then appears to go through the center of curvature. So it's called center ray in this case, okay? Get reflect back because that's the normal direction. F ray appears to be hitting the focal length, but it doesn't, right? So you extend it, then it will be appearing to be going that way and comes back, okay? So in this case, you always, so you can see those three reflected rays, they do not intercept on the side of object, right? They actually, if you back extend, then they will also intercept behind the mirror at this common point. So this is where the image then is forming. So you get actually a virtual image, okay, but upright, okay? So virtual image is upright. And your side mirrors are made of the your car made of the convex mirror. So if you look carefully, there's always a fine print says your image appears to be smaller than they actually are. So you get a smaller image in that sense. Okay. All right. So let's now take a look at the relationship between the distance of the object to the mirror and then distance of image to the mirror, okay? And also we'll also look at the relationship between the size of the images compared to the size of the object, which is denoted as the height of the object and the height of the image, HO and HI, okay? DO is the distance from the object to the image to the mirror, DI is the distance from the image to the mirror. So in this case, we'll pick array, okay, any ray, not necessarily the one of the three, but any ray in this case. So let's pick this ray from the top of the object to hit to the center of the image of the mirror. So you'll get reflected back, okay, and your image will be some point over there. So this angle is theta, and this should be the same because law of reflection says so, okay. We'll pick another ray that's from the top of the object. So then that ray goes to the center of curvature, hit this mirror, okay, and get reflected back. Okay, so it should be coming back in the instance direction. The image will be somewhere here. Okay, think about that. So we are kind of separating these two rays in different pictures because then we actually will use the geometries of each of the ray has to do with the object and images separately, okay? All right. So in here, you get actually a larger triangle here, right angle triangle, okay? That formed by the height of the object and then with the principal exit, and then this ray. And then the smaller one here formed by the height of the image and the principal exit with this reflected ray, okay? So these two are similar triangles. That means they have same internal, or the three angles are the same. So this one and this one is the same. The 90-degree angle and the 90-degree angle are the same. So then the remaining angle should be the same because all three angles in a triangle should add up to be 180, right? So if two of them are the same, then the third one from each triangle should be the same as well. Okay, so these two are similar triangles. And look at this triangle formed by the height of image and then this part of the principal exit and this ray, and then also this smaller triangle formed by the image and then this one and this. Okay, so they are also similar triangle because this is the two same angles and the 90 and 90 are the same. So then the third angle from this triangle will be the same as the third angle from this second triangle. Okay, so these two are also similar triangles. So for similar triangles, we have two pairs of similar triangles, then we can actually write two equations, okay, out of the two. So we could do the ratio of the size, okay, so let's take a look on the geometry. So for the first one, if you look at the PowerPoint slide, the first triangle, if you do DO, so this side over this, then it should be equal to DI, this side over this, okay? So DO from first triangle on the left, okay? So this is equal to DI over HI. The second angle, the second triangle, if you do Now in this time, if you look at if you do the dO minus R over HO, so look at the geometry, that should be equal to R minus DI over HI. Okay, so because this side will be, you can see from, I think that everything's labeled very clearly, so you can see that. Okay, so if you do dO minus R over HO, that should be equal to R minus dr over HI. Okay. All right. So we get these two equations from the two pairs of triangle. Let's take a look on this. So dO over HO, so we'll write this as two fractions. dO over HO minus R over HO equals to R over HI minus DI over HI. Okay. All right. So from this equation, we know DI over HI, right, is equal to DOH over HO. So this then can be replaced by DO over HO. Okay. So minus DO over HO, and then this is positive. So these two this guy can go to the other side. It becomes twice of DO over HO, right? And that equals these plus that. So be R over HO plus R over HI. Okay. If you combine these two together, they become HI. Okay. And then on the top, you have R times HI plus HO. Okay. That equals to twice of DO over HO. So there's a little bit of cancellation here. HO cancels. Okay. And we can manipulate this a little bit. So we can divide both sides by R. Okay. So R and R cancel. We can divide both sides by 2. So we can divide by 2. So these two and these two cancels. Okay. All right. And then now we can multiply both sides by HI. So just a little bit of things here. HI will cancel the HI. Okay. And let's see. All right. Okay. So then now divide everything by HI plus HO on this side and then also on this side. So HI plus HO. Okay. All right. So actually, so then this goes away. Actually, I think I will did not have to do this. So this stays there. Okay. So then this would not be there. Okay. So R will be staying there. So now let's take a look here. So we'll have then HI dO over HI plus HO equals just R divided by 2. Okay. We should have R there, so this R would go away. So R divided by 2. All right. So for the focal length, we know that's equal to 1/2 of R. Okay. So this guy on this side then is 1 over F. Okay. So so in this case, so this is actually F, not 1 over F. Okay, so we can just flip everything. So let's do flipping everything. HI plus HO over HI DO, okay, equals to then, so if this is F, then F over 1, okay? This is F. All right, so now here, we can separate these two, right? So you can have HI over HI times DO plus HO over DO and then HI, okay, equals to 1 over F, okay? So HI cancel. So you get 1 over DO on the first term plus HO over DO. Now it's a little bit far away, but if you recall here, HO over DO should be HI over DI, right? So then we should just write HI over DI, and then there's still HI there. So that goes away, equals to 1 over F, okay? So, or actually here, sorry. So HI over DI is HO over DO, okay? So H and HI will cancel. So 1 over DI plus 1 over DO equal to 1 over F, okay? Equals to 1 over F. So this is the mirror equation, okay? So then the relationship between DO and DI is simply 1 over DO plus 1 over DI equal to 1 over F, okay? We derive this from the concave mirror, but it also applies to the convex mirror, okay? This equation also applies to the convex mirror as well, okay? So the mirror equation, okay? And then where F is equal to 1/2 of R for the concave mirror, for convex mirror will be minus 1/2 R, okay? So for the notation, convex mirror, you will have minus negative focal length, concave mirror, you have positive focal length, okay? All right, a little bit summary. So when we had image formed by convex and concave mirrors, so if we have convex mirror, you always get a virtual image, reduced size in size upright, okay? For concave mirror, it really depends on where your object is sitting at. So if you are beyond the center of curvature, you get inverted, reduced real image. And between F and C, you get an inverted, enlarged, and real image. Inside the focal point, you get upright and image, okay, and then it's virtual. And or between mirror and which is inside. So between mirror and the focal length, so upright, enlarged, and virtual. And you guys can actually work on the geometry to find where exactly if the object is sitting on the center of curvature, okay? And then so do the sketch out and then compare to the conclusion from here. So it should be easy to do, but that gives you a extra practice on the forming the image, okay, to find the image. So in that sense, on those special locations, center of curvature, on the focal point on the side that is just beyond the focal point, or on the focal point on towards the side that's just inside the focal point. Okay, so those. All right. A quick review on the sign conventions for the two mirrors, concave and convex mirrors. So your focal point is positive for concave mirrors because the concave mirror can form real image, okay? Focal length is negative convex mirror because convex mirrors always form virtual images. Magnification is positive for upright images. It's negative for inverted image. Okay, so in that sense, so HI will be positive. Okay, for the upright image, HI will be negative for the inverted image. Okay, image distance. DI is positive for images in front of mirror, real image. DI is negative for image behind the mirror, which means a virtual image. Okay. DO is positive for object in front of mirror, real object. DO is negative for object behind the mirror. Okay, so that refers to if you have multiple mirrors. Okay. All right. So magnification, as its definition, is defined as HI over HO, the height of the image divided by the height of the object, and it's equal to minus of DI over DO. Okay, so when you get real image, remember HI is minus, okay, because it's upside down. Okay. All right, let's take a look on this example here. So it says a concave mirror produces a virtual image that is 3 times as tall as the object. If the object is 16.0 centimeters in front of the mirror, what is the image distance? What's the focal length of this mirror? Okay, so it tells us a few things. Let's assign them to the quantities. So first, it says a concave mirror. So concave mirror, F should be positive, right? So let's just put that somewhere there. It says if the object is 16, so DO is 16.0 centimeter, okay? It's asking you what's DI. It also tells you a virtual image is 3 times as tall as the object. So that means HI is 3 times of HO, okay? All right. So what can we do about this? So we know that image equation, okay, 1 over F. We know magnification equation, HI over HO, also equal to minus DI over DO. All right, so look at these two equations, okay, we are given DO. We are given HI equal to 3 times of HO. Okay, so it looks like we can have HI over HO, actually that equal to 3, right? Because move this guy to the other side. So HI over HO then equal to 3. So this is 3. So if this is 3, this guy's given, so it looks like we can find that. Okay. So we can set 3 equals to minus DI over 16 centimeter. Okay, so that tells you DI equals to minus 48 centimeter. Okay. So it's negative. That means it's a virtual image, and which is consistent with the problem. Okay, so that's good. All right, so we have solved part A. Part B says, what's the focal length? Okay, so now we have DI, we have DO. Looks like we can use this mirror equation to find F, right? Because F is only unknown there. So 1 over DO, which is 16 centimeter, plus 1 over minus of 48.0 centimeter equal to 1 over F, right? So then you'll just do 1 over 16 centimeter minus 1 over 48 centimeter, right? And then everything inverse that equals to your F. So this turns out F to be equal to 24 centimeter, which is positive, right? As we have expected. Okay, so it looks like we have solved the problem. So for imaging by mirror, so there are 2 main equations here and this one. Okay, so you pretty much just play around with those two, and you should be able to find out the things. One thing role you might want to do about this problem is to sketch. Okay, so you'll see then. It says the image is 3 times taller, as tall as the object. So that means it indicates it's actually a virtual image. Okay, so you can draw a principal exit and then this guy here. So if you have your object somewhere here, typically you use an arrow, okay, for your object. So it says 3 times. So maybe think about somewhere here being 3 times larger. So center of curvature should be somewhere here. Okay, so if you say this is your center of curvature, if this is 3 times, then it's about 3 times. Okay, so of this. So somewhere here, that's your image, a dash image. Okay, so in that case. All right, so then, yeah, so this is a center curvature ray, hit there, comes right back, right? So that's where you will have that. And maybe a P ray. So this is a C ray, maybe a P ray here. It will reflect back as, so you connect these two together and then going back somewhere there. Okay, so that will be somewhere, will be your focal point. Okay, I don't think I have a perfect drawing here because focal point should be halfway between center curvature to the image, so somewhere there. All right. Yep. So that's your sketch if you want to have it. Okay. We'll stop here for today, and then we'll come back next time. So see you guys later. Bye.